All right, everyone. So welcome back, and we are going to now go ahead and get started today a little bit. If I can get this guy here. Good. Let's move this out of the way. All right. We're going to get started with our first lecture. So one of the unique things, and we can kind of talk about it a little bit. Sorry for moving all these things around, but that's just the way it goes. We're going to talk a little bit about the structure of this class. And one of the unique things about materials and materials engineering is we are going to be dealing with lots of kind of unique things that are particular to actually specific the discipline of material science and engineering. So specifically, we're going to be working with things called length scales. Length scales. And we're going to be dealing with quite a large order of magnitude change in terms of our length scales. That's another term we should be thinking about. Order of magnitude. We'll come back to this. Order of magnitude. Order of magnitude is basically a 10 times difference. Again, I'll say that we get back to it, and then I'll say that we're going to do it now. But anyway, just stay with me. So, length scales, we're going to be looking in this first lecture at the atomic length scales. So basically, we're going to be looking at kind of atomic bonding between atoms and atomic structures. That is on the order of angstroms. Angstrom is, again, and we want to always make sure we use our units. If we're looking at length, it's going to be 10 to the minus 10 meters on the angstrom length scale. So if we're looking at bonding between atoms, you're going to look at that length scale. In the next lecture, lecture 2, we are going to be looking at basically crystalline structures and non-crystalline structures, amorphous structures. Those, when you're looking at clusters of atoms and crystalline structures, that's going to be more on the nanometer length scale, 10 to the minus 9 meters. Then, when we look at defects, we're going to be looking at grain boundaries and some of those things, and those can be at the micrometer, 10 to the minus 6 meter length scale. And then eventually when we get into mechanics and you're pulling essentially systems, you can vary between millimeter, which we know to be, excuse my handwriting, 10 to the minus 3, all the way to meter length scales. So if you look at this, we're going to be changing essentially or exploring material structure on the range of 10 orders of magnitude shifts. And so that's incredibly critical. That is very, very unique in a class. This is kind of this hierarchical structure that we're going to be seeing. It's this multi-scale length scale, and it's very, very unique in material science. And this order of magnitude change is important too, because when we're looking at materials, we're looking at changes that are on the order of magnitude. A lot of disciplines of engineering, if you get a 10% increase, that's great. But for materials, we're looking at those big changes. Another thing, again, that we will be talking a lot about is oftentimes we're going to be looking at how does a material scale? So if you see me, like, is it scaling to linearly? Is it scaling to a power? Kind of the scaling type of behavior is often more important than these prefactors here. So that's just something to kind of think about and consider. So again, since this is on video, I'm going to take all of this, all my hard work, and delete it in a second. How are we going to organize this class? Well, I can tell you my course schedule when I was an undergraduate student: 3012, 3014, 3016, 3022, 3024. This is for a material science degree at MIT when I went to school, ages ago now. 3032, 3034, 3042, 3044, and then I took 3063. I took some other courses. But anyways, so this course in material science was basically structure and thermo. This was a lab course. This was Mathematica programming course. This was kinetics. This was electrical, optical, and magnetic materials. This was mechanics of materials. This was kind of a biomaterial course. This was senior design. You'll take this in your other majors. You don't have to worry about that. And then this was heat transfer and fluids. We will not be covering that in this course. And then here is polymers. So if you look at the structure of our course, we have our first lecture, which is Introductory to Bonding. So that kind of is related to structure. Lecture 2 and Lecture 3 are very related to structure. Thermo is related to our Lecture 4, which is involved in phase diagrams somewhat. So hopefully you've all taken some thermodynamics, but if not, we're going to learn it here. What else do we got? Lecture 5 and 6 is going to be getting into mechanics. Lecture 7 is about electrochemistry, which is also a little bit of thermo. And Lecture 8 is polymers, which is right here. And biomaterials here. They kind of are related here. We have, and I have in our textbook, a separate chapter on kinetics, but we will not be getting into that in this course. There is also an additional lecture that I'll provide on electrical, optical magnetic materials, but again, that's not becoming this course. And we are going to be running a very, very similar version of the labs that we learned when I was a student. So it is going to be... We're going to pack in this single semester basically 4 years of undergraduate material science. Are you ready? Are you with me? Don't worry. We'll handle this all together. So I will see you all in the next lecture, and we will get into one of my favorite kind of concepts. This is materials tetrahedron. Thanks. Bye.